Okay, so today we're going to be still working on proof by induction. But specifically, we're going to be talking about sigma notation. And the reason why I'm taking a specific focus on this is because in last year, this was a little thorny for some. And I wanted to kind of make sure that we didn't have the issues this year that we had last year. Because in fact, induction doesn't have to be incredibly difficult. It's a lot of algebra, okay? And in fact, most of this course is just a lot of algebra. All right. So first, let's talk about the goal of this. So we're going to have some summation, and at our induction step, let's do this first of all. Let's show, this is an example for r equaling 1, r. All right, now if you take a look at this, what are we actually really looking at here? We've seen this before. Might not have seen it exactly in that particular form, but we just spent a whole section talking about the summation of things. So that's one way that you can work these things, and you should, especially because in the very beginning of the proof, you have to convince yourself that it's true. So, I mean, it's very difficult to prove something if you don't believe it. So these are 1 plus 2 plus 3 up to n. And we've seen that. That's an arithmetic sequence of a common difference of 1. And so we've seen this format. We know this equation. And this right-hand side is the first of the two equations we got for that one, when we know the first and the last term, because the first term is 1, the last term is n. So this is truly straight out of the formula. But we've never really proved it. I mean, I illustrated it when I said, you know, Gauss figured out that if he could fold the number line onto itself, you would get these brackets and everything would add up nicely, but we never really wrote it in a formal sense and proved it, but here we will. Now, what we need to do, if you think about this, first of all, let's do the full test and do the base case. So base case is what? N equals 1. So the sum of r going from 1 to 1 1 is equal to 1/2 of 2, which is equal to 1. So the base case holds. All right, now, the goal of this is the k plus 1 case, okay? So the k plus 1 case looks like now remember, to get the k plus 1 case, all we do is go back up to the original assumption, the original statement, and show and replace n with k plus 1. Okay, now, to do this, we're going to start with the assumption. Now, I know that somewhere in your notes we did actually use this proof on the very first day of doing induction, when I just crash coursed you into it. Now, the trick here, the difference between what you already have in your notes and this is that this time we're specifically using sigma notation, which in the first, if you look back in your notes on that day, we didn't use notation. We just said 1 plus 2 plus 3 plus 4 all the way up to n, and we just left it as this series of numbers, and we didn't use the formal sigma rules. And that's what is different about it now. Okay, because playing with sigma notation has its own set of rules to it. And if you're not comfortable using sigma notation, hopefully you will be more so at the end of today. Sigma notation is ubiquitous in mathematics. Okay, so it's one of those things you just kind of have to wrap your arms around and say, okay, what am I looking at and what am I used to seeing? So we start with the assumption. And the assumption is replacing n in the original function with k. And our goal is to get to the k plus 1 case. All right, now a couple of things right off the bat. Some rules. This r is a dummy variable. It will never be involved in your final answer. It will never be substituted. It is contained entirely within the sigma notation. Do not let it wander, okay? It never changes in your notation. You'll never have to, you'll never put k down here in the bottom of your sigma notation. This will not change. None of those things will change, okay? So leave r alone, okay? R is a counter. That's all. Now, the trick here is to know how to change that upper bound, because that's really what you're wanting to do. Okay, nothing else on the left-hand side is going to change except the k is going to go to k plus 1. So, let's think about this for a second. Off to the side, if I had this, just for a moment. Okay. What I'm going to do is I'm going to expand that so we can look at it and really begin to understand what it is we're dealing with. So 3 times 1 squared, 3 times 2 squared. All right. If I wanted this, if that's really what I wanted, and all I had to start with was the upper line of the upper equation, how can I turn that upper equation, look at the right-hand side, and say to yourself, what would the sixth case look like? What would go here if it was 6 terms and not 5? What would you put there? Exactly. So, the only difference between this and this is this. Okay. So, I can do this. So just by adding a term, the next term, I can change the upper bound of that sigma notation. Does that make sense? Okay. So, this guy, this left-hand sigma notation, is 1 plus 2 plus 3 all the way on up to k. What do I need to do to turn that into the k plus 1 case? add what? Add k plus 1. And now magically, not so magically, the left-hand side becomes exactly what I want it to become, the k plus 1 case. But remember, I added something to the left, which means I have to add something to the right. So at this point, what should I do? My left-hand side is golden. I don't have to fool with him anymore. Now I got to get the right-hand side to look like it's supposed to look. So that's what it's supposed to look like. What am I going to have to play with? What should I do? Currently, my right-hand side does not look like it's supposed to. Okay. In the notes from the other day, we talked about trails of breadcrumbs. Okay, so if you're stuck at something, one thing that you can do is go backwards, like we talked about. But before you even do that, you have two multiplied terms in your target. You have a giant pair of parentheses and a... All right, that's what your goal looks like. Right now, if I walked up to this on the sidewalk, the first thing I would see would be a product. It's the product of two things, okay? Both of those two things have degrees of complexity to them, but that's not the point. That object right there is a product. This object right here is a sum. So absolutely, the first thing that needs to happen is I need to not be a sum anymore. So how do I deal with that? No idea. You guys really hate fractions, don't you? What?
The second term multiplied by 2 to put it over 2.
Okay. Common denominator. Now I walk up to that thing and I see a quotient, which is the same thing as a multiplication. And now we distribute. At this point, you might be thinking to yourself, all right, maybe I need a trail of breadcrumbs in here. So let's go and play with my breadcrumbs. That's the target. Whoops. Sorry. That's the new target because we're going backwards. But we had k times, sorry, strike that. It was k plus 1. Our final honest to God answer is supposed to look like this. Right? That's what our final answer is supposed to be. So let's play with it. Let's just toy around with it and see what happens. Wait a minute. That looks vaguely familiar. Right? That's our trail of breadcrumbs. So all I really have to do right now is multiply that out and then work backwards, and I'm done. So, oops. So the only difference with these kinds of induction proofs is knowing how to play with the left-hand side. Principle of mathematical induction. And we're done. That's optional. Yeah. Hmm. All right. So there are three summations that are kind of like standard garden variety summations that you would probably need to know. And we'll cover those. Also, um, have you guys worked with some sigma notation extensively, or in? You don't do a lot of it, do you?
No.
All right, so let's go into that. You know how they work, where you start, where you stop, what you do. Okay, I did write that down, didn't I? I think somewhere in your notes. But just for the
Explain there.
yeah, so the properties. Properties of sigma notation. Actually, I'll do this. Yes. Okay. So I don't know if that's in there already. It is? Okay, that's good. Um, and then I hope I've said that constants can be pulled out. Let's just put something there. Any constant can be pulled out as GCD. Um, added terms can be broken up. Um, stop me if I'm wasting my breath here. So added terms can be broken up. Not multiplied terms, but added terms can be broken up. Um, what else? What other properties did I discuss? Or have I? I think that's it. That we know. Okay. We good? Yo. Oh yeah. Yeah. Exactly. Um, these are some. Actually, these are important. That's true. Um, and all right. Um, yeah. I think that's all there is that we need to worry about. Okay. We good? Everyone happy? Thrilled a minute. So let's do another example. Actually, I will give you these three that are very, very useful. You are welcome to use these in your proofs. That's 6. So that was the one that you got the other day. We'll do that if. Okay. So deriving these is not as easy as it may. Well, some of these are pretty straightforward to derive, but some of these other ones that you'll be getting, they aren't very easy to derive from first glance. However, they can be proven by using induction. So even though we may not know exactly how to get to that, what that summation equals, well, if we know what it equals, we can prove that it's true. So let's do this one and this one, and then we should have all of our tools in our hands to be able to handle other stuff. Okay? Awesome. So um, okay, hit the boards, and we'll all do the first one together. All right. So get your markers, grab whatever you need, make sure everything works. You know, my HL2s hide them.
The good ones?
Yeah. They all have their hiding places around the room.
There's one right there.
Yeah, like behind the monitors. Yeah. So if there's a good marker hidden, don't fool with it. Someone's going to come looking for it. Just hide your own. All right, so let's do a base case. Base case is n equals what? 1.
Really on one shot. If you're racing.
Check that the base case does hold. So does the base case hold? Oh, I'm sorry, that's r squared. Yeah. Yeah, r squared, my fault. Are we reaching consensus that the base case holds? 1 squared is equal to 6 divided by 6, right? All right, so the base case holds. Yes, I am lazy. Don't be lazy in yours. So the base case holds. All right, so now write down what you think the k plus 1 case looks like. What does the k plus 1 case look like? What does the k plus 1 case look like? Yep, that's looking good. All right, excellent. Seeing a lot of right answers, but you lost your segment notation. Your left-hand side? Yeah, yeah. Okay, yeah, don't forget to make sure that the bounds are correct on the left. They start at 1 and go to k plus 1. Good. All right, so the k plus 1 case looks like this. All right, that is very long-winded. We know that. It's not a problem. Lots of nested parentheses, but it's not the end of the world. Okay, so now write down the case. So to do this, we begin with the assumption. So write down what the k case looks like, and let's get to work. Yeah, give yourself room. Unless you want to take a picture of your work when you're done, it's fine. But this video is being recorded. It will be put up on YouTube. Eventually, there will be a link somewhere posted on my webpage if I can ever have time to work on it. Okay. Good. So, it's a heck of a lot easier to attack the left and then attack the right. Okay, attacking the right and then playing with the left, ooh, that's a lot of work, man. That is, and it is an inefficient use of your time. It's much easier to attack the left and then say, oh, this is all I got to do to the right. Boom. Okay, so what is missing from this so that I can turn it into the k plus 1 case? Well, what does the k plus 1 term look like? K plus 1 squared. Because remember, what is this but 1 squared, 2 squared, 3 squared, plus 1 plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared, all the way up to k squared. So the next term would be k plus 1 squared. And remember, you're adding something to the left, So you don't want to forget to add something to the right. Otherwise, you won't have anything to work with. And you'll be mistreating your equal sign. So now that I've added the k plus 1th case, I can modify the bounds of my on my sigma notation, and now it becomes and now all we have to do is perform a small miracle on the right. Okay. All right. A small miracle might be necessary. So let's first figure out what we have, what we're missing, and what's going on here. All right. First of all, we all know what the target looks like. And this is a way that you can begin attacking things not just of this nature, but algebraic problems in general. There are certain features of your current situation and features of your target. First of all, they both have what in them already? Well, yeah, there's k plus 1s in lots of places, but some of that stuff is going to change, and right now we got one thing going for us. They both have a 6 in them, so we don't have to fool with that. That's good. So let's put that in our happy place and say, great, that's wonderful. All right, now, one thing that we have on our current scenario is that is totally unlike our target is what? More, not just k plus 1, we have an exponent. Okay? That is not in my answer. So that should be the beacon to say, let's attack that exponent because it's got to go, right? So no matter what, I don't care what our trail of breadcrumbs is going to do, that's got to go. So let's expand it immediately and then fool with. Yeah, but remember too, and by the way, guys, there are some, if you do this, and I've talked about this before, if we write this out and then multiply, do the first, outer, inner, last, whatever you call it, double distribution, you're wasting your time. Because this binomial squared should be second nature, okay? There are some expansions that you should just know. And a perfect square looks like, all right? Okay, so first one is squared, the two numbers are multiplied together, then multiplied by 2 in the middle, and then the last term is squared. All right, so okay, at this point, a trail of breadcrumbs might be useful. But what's one thing that you know you've got to do? Yeah, because you know what? My answer does not have added things in, outside of parentheses, right? So no matter what, I had better make this thing look like one object, okay? So to do that, like we did before, let's use the common denominator and be able to put this whole thing over 6, and then at the very least we know we're close. Now, I went ahead and multiplied out the 6 to all of those 3 terms. That may not be the way to go. I don't know. We won't know. Because, remember, when you do your trail of breadcrumbs, it just looks like you magically came up with the perfect method, okay? Because you know the trail back home, all right? So, let's go to a trail of breadcrumbs and see what we got. So, we start with what when we're playing with the trail of breadcrumbs? Yeah, we start with the end, which is the k plus 1 case. Um, right? That's what the k plus 1 case looks like. And yeah, I cleaned up my middle parentheses. And let's keep going. Okay, so that looks somewhat normal. Play with it and see if you can come to a happy place in the middle of the woods. And okay, so what I've just written in the upper right-hand corner is your goal at this moment, is to hopefully find something that looks sort of, kind of, maybe like that. All right, or at least be able to find a way in. So what do you think? How you gotta play with this guy. What do you want to do with him? What can you do with him? Yeah, multiply the living daylights out of everything and see what you get. There's one term in there that you might not want to fool with. Which one? Hmm? Well, look at where you are and look at where you're going. Yeah, you have a k plus 1 in both of them. You see? So that might be unnecessary to play with. Okay, because at the end, we might have to pull that guy back out again. But we don't know. Who knows, right? Because let's also remember we got to deal with the fact that we've got all added things. We have to turn all of that into a multiplied thing. Okay, so we don't know yet. But multiply the second and third together because we know that those have to change, right? See what happens with them first. Does it get us anywhere? Hmm? Hmm? Sure, you can pull out a GCD there, can't you, though? Yeah, I don't think I don't think you pulled your rabbit out. That's why you have a GCD of a 2. So, you wind up with this, k plus 1, 2k squared plus 7k plus 6. Okay, well, the fact that I've got a 6, that makes me a little happy. Okay. But at this point, you got like, okay, so sorry, Ronco, I still got bupkis. you know? Yeah, you know what? Let's just multiply the living daylights out of all, see what we got, because apparently they're supposed to be equal anyway. So let's just see what happens when we blow it all up and, blow it all to pieces and then see what the pieces look like, and then we may be able to put it back together again. What happened when you multiplied it all out? Is that what you guys got when you multiplied it all out? Okay, yeah. By the way, notice how I multiplied them out? Look familiar? Yeah, a lot nicer than doing all those distributions all over the place. Just fool with the coefficients because you know what the exponents are all going to be. So just work it like it's multiplication. Makes life a lot easier. So what do we got? We got 2k cubed plus 9k squared plus 13k plus 6 all over 6. All right, now somehow, somewhere, it's supposed to be that thing. Okay. Yeah, so let's blow that up too and see what happens. So we've got a trail of breadcrumbs inside a trail of breadcrumbs. Okay, it's like we're sending out scouting missions. No, well, we just see if we can find a path, So we know that they're supposed to be equal, right? So somewhere there has to be a common meeting place. So I'll do it this way. So we wind up with 2k squared. Okay, so I just multiplied out my first two of them, right? Right? And now we oh, okay. Oh yeah, it's squared now. Right. Yeah, isn't that kind of weird? So, and if you look, we've got all of our pieces in here now. So, congratulations, you have found a common place in the middle of the woods. It's time to go back home and hopefully not be sent out to die tomorrow morning. All right, so now, at this point, the math is done. The wording and workup is not. So, when you write this thing up, here's what you're going to write. First of all, now you don't have to do this on your boards because I know it's an enormous amount of writing, but let me just show you what it looks like. Right? Actually. Okay. Yeah, it gets big, and we still have like a paragraph of text to write after it. But here's the point. Let me show you at the very end what it looks like, because this is why we do the trail of breadcrumbs. Okay, from here, okay, getting a common denominator, yeah, sure, kind of like a kind of like a normal thought process. We have terms we need to put together. Let's find a common denominator, and then multiplying this thing out, that kind of looks normal now, and then putting it into this form, that's a little odd, and then saying to yourself, oh, sure, I'm just going to factor out a GCD of a k plus 1. Of course, because I know that it's there. Right, sure. Yeah, so, if I give you, a cubic polynomial and say, find me a simple binomial GCD. Bronco. Such things are beneath me. No, k plus 1, of course, factor it out, and then, of course, you get that. So it looks like there's this moment of genius, okay? And then you're like, oh, of course, oh, pshaw, this is nothing. And then finally you're done. And so that's the whole idea, all right? Now, there are some important tools to put into your toolbox when you're doing these. First, how to look at your target and your starting position and say, what is already good? What is obviously got to go? And what is what's the general form of my answer? The general form of my answer, to get rid of the square, to turn it into a product, happy that we have 6. When you heard me say, when that 6 popped up when I was doing the trail of breadcrumbs, I was just like, hey, that's a warning that I'm on the right track. If I had landed with, the 9 and the 13 might be a little daunting because you're just kind of like, well, wait a minute, there's nothing like that in my answer. But if I was working this thing and all of a sudden I came up with negative 54, I might be a little, well, maybe not, because that's 9 and 6, but the square root of negative 54, that would warn me that something is dreadfully wrong, okay? So there are kind of like mile markers and lampposts along the way for you to say, things are looking good, things are not, okay? But like, for example, if your 6 in your denominator changed somehow, no. Go back, because that was a happy thing, and we didn't want to lose it. Now, by the way, take a look at the boards and realize, first of all, that's a normal work. Be proud of yourselves for it. It looks really cool. And it kind of makes me feel like I'm back at the institution before they stopped me to write on the wall. Okay, next. So, okay. All right. All right. Yeah. Okay. So I'm going to, yes, of course, there's the paragraph underneath this thing, which we have to play with. But I think we all kind of got the point. So I'm going to end this episode of the Ronco Show. This episode has been brought to you by the principle of mathematical induction and the number 6.